Good morning, everyone. It is 8 a.m. in California. It's time to start. Good morning to our colleagues in North America. Good afternoon to our friends in Europe, and good evening, and also in Middle East and Africa. And good evening to our patient TinyML enthusiasts in Asia and Far East. So as you know, global TinyML meetup community continues to grow, and as of today it includes almost 2,000 people from more than a dozen of different countries all over the world. Hope you're all well and healthy during these days. Again, we welcome you and thank you for joining episode 3 of our bi-weekly TinyML webcast series. My name is Evgeni Gousev. I'm from Qualcomm AI Research. I lead TinyML in Qualcomm, and I'm also one of the organizers and one of the co-founders of TinyML, which we started about a year ago. It is my pleasure to introduce our first sponsor for the TinyML Talk webcast series. It is H-Impulse. It's an international startup with 2 offices. One office is here in San Jose, in the Bay Area, and the other is in Amsterdam. H-Impulse provides a developer platform for ultra-low power machine learning from design to deployment at scale. So if you're interested, please visit the website, himpulse.com, if you're interested to get an account there. And if you're a developer, H-Impulse goals is to help you to start and maximize your success with TinyML. I think it's quite exciting from us to see this interest and companies like H-Impulse investing into the ecosystem development and supporting TinyML. I think this is going to benefit all of us. More sponsorship spots are available. So if you're interested in supporting TinyML and in exposing your company to this fast-growing ecosystem, please contact Betty at betty@tinyml.org. And I think our intent is to keep the TinyML talks free of charge for all the participants. So sponsorship is quite important and appreciated. Our next talks will traditionally take place in 2 weeks. So again, we are going to have 2 presentations. So one presentations will be given by Hans Reischerhoff from Facebook Reality Lab. So he's going to cover TinyML in the for AR applications. And the second will be given by Jamie Campbell from Synoptics on using TensorFlow for microcontrollers. There is a little bit of a change due to scheduling. It will be on Thursday, May 13. And as usual, you're going to see announcements and information about the pre-registration by email and via social media in a couple of days. So kind of keep an eye on this. My pleasure to introduce a presentation from Europe now, from Octonion. Also very interesting topic. It's on unsupervised collaborative learning for TinyML. And the presenter today is Alexander Eroma. So, Alexander graduated from Belarusian State University on Informatics and Radio Electronics in Computer Systems and Networks. And then he received master's degree in Computer Science and Computer Networks and Compilers. And right now he's working also towards PhD in this area. He is the author of several articles in the field of machine learning. And he works for Octonion. And at Octonion, he's responsible for machine learning and deployment of complex algorithms, high performance code, and architecture of machine learning. Okay, Alexander, please go ahead.
Thank you very much for introduction. So hello again, everybody. My name is Alex, and I'm the intelligence team lead in Octonion. And in Octonion, we develop an IoT platform with AI capabilities at the edge and in the cloud for various applications. And in this presentation, I would like to share our approach for collaborative unsupervised learning in the application of vibration analysis and machine condition monitoring. So for better understanding of the approach rationale, let me briefly describe the problem. The aim is to provide a tool set for equipment manufacturers and maintainers for automatic recognition of machine condition and operational modes in the absence of priori knowledge about the machine. Equipment vibration here consider it as the source information, and the clustering algorithms consider it as the appropriate tool. The idea of sharing received knowledge from one to many machines seems natural as a user operates with a fleet of equipment. In considering approach, multiple edge nodes, which are represented by microcontroller-based devices, are connected to the cloud using star topology. Each node is continuously performing vibration pattern recognition and contribute newly learned patterns into the shared model at the cloud. Cloud application responsible for making corrections in the centralized model and model patches delivery across all nodes in the topology. Let's consider some major aspects of edge data processing first. Edge node is responsible for a few important things. First of all, recognize known and novel vibration patterns in unsupervised mode. Then trigger abnormal vibration alerts and push received knowledge into the cloud to update shared AI model. And also receive and store vibration knowledge from other devices. Let's have a brief overview of data analysis pipeline at the edge, which has the following major steps. First of all, signal filtration stage necessary to remove low frequency variations and constant component of the accelerometer. Signal features calculation necessary to recognize vibration patterns and construct the vibration pattern descriptors. Stationarity classifier used to filter out signal vibration spikes from the classification stage. Pattern classifier makes a decision if observations represent known or novel vibration patterns. And clustering procedure used to construct vibration pattern descriptor based on the past observation in unsupervised mode. Due to the lack of time, let's focus only on the most important parts of the pipeline in the next slides. At the initial stage, we evaluate various features on top of the raw acceleration signal. As seen in this example, source signal processed over a sliding observation window, and the observation window itself divided into multiple intervals, x1, x2, x3, and etc. We calculate features for each of these intervals and consider the intervals as a set of objects in further clustering step. Here you can see an example of calculated features for each interval. And for simplification of understanding, let's just consider two-dimensional feature space. Once we have evaluated features for objects in the current observation window, at first we try to classify this observation window across known patterns. Saying abstractly, the vibration pattern represents the convex geometrical object in multidimensional geometrical space. So the classification task is to find the largest intersection of the geometrical object constructed from the current observation window across known vibration patterns. In case if a set of objects under the current observation window were not classified as a known vibration pattern, we need to perform a vibration pattern construction. For that purpose, observed objects considered as the source data set for k-means-based clustering among n groups, where samples belong to the same cluster are similar to each other, and samples belong to different clusters are not similar to each other. Taking into account that at this step, we deal already with relatively stationary observations, normally resulting allotment represents one cluster with significant number of objects, and the rest clusters with small number of objects. The goal of clustering here is to filter out outliers from the study population. So only typical samples used to build pattern descriptors. So this example demonstrate possible resulting allotment. As seen in the example, clustering procedure produced one cluster with significant amount of objects representing actually the desired vibration pattern, and another small cluster representing the data outliers. Desired vibration pattern allocated as a convex geometrical object which covers the shape of all objects in the largest cluster. And in this particular case, we use a box shape to produce object. Now let's consider some principles of sharing knowledge across multiple nodes. There are several major concepts of this. First of all, each device holds a local instance of the model. Cloud application responsible for shared model storage, model correction, and versioning. Shared model complemented with new patterns learned at the edge. As seen in the flow diagram, as soon as any device recognizes novel vibration pattern, this pattern is sent to the cloud to contribute into the shared model. Cloud application constructs model patches to deliver learned patterns to other edge nodes. Let's consider an example of knowledge distribution. Initially, device 1 recognizes pattern P1 and P2. Also, please note that geometrical representation shown in the slide. As soon as pattern descriptor received in the cloud application saves this information into the centralized storage and share this knowledge to device 2 and device 3 and so on till device n. As seen in stage 2 and stage 3, the same procedure takes place for devices 2 and device n. One of the key aspects of this collaborative learning approach is to produce is the procedure of model correction done in the cloud layer. The rationale for this is that in real world, each machine mechanically unique. So n similar machines may have n similar at global scale, but different at local level vibration patterns corresponding to the same machine operational mode or condition. And to overcome this disadvantage, model correction procedure takes place, which consists in applying of additional clustering to all known patterns from all nodes. So the similar vibration patterns recognized independently on different nodes can be merged into a common pattern. So let's consider an examples of this model correction procedure. As seen as a figure, though patterns P1 and P3 recognized as different patterns at the different nodes, on a global scale, they are quite similar, and the same applicable for patterns P2 and P5. Please also note that in this example, we see kind of overlapping patterns. However, in real life, it's also possible to have a group of patterns which are close to each other but not overlap, but also represent the same machine behavior in the global scale. So to solve this problem, we apply patterns clustering procedure to find out the groups of overlapping or tied patterns. And once clustering complete, the allocated clusters consider it as a new descriptors of vibration patterns by a union of cluster elements into the covering geometrical object. and then appropriate model correction patch constructed and sent to all edge nodes. So in this way, a major idea of considerate approach is to perform local scale unsupervised vibration pattern recognition at the edge nodes using vibration samples clustering, and then to generalize knowledge received from multiple nodes by application of pattern clustering procedure at the cloud level. In general case, described approach may be applied not only to vibration data, but also to different data sources, like sound or images, for example. Also, you can check out the dedicated demo using following link. And many thanks for your attention, and I will be glad to answer your questions. And also, please feel free to contact me by mail. Thank you.
Okay, great. Thank you, Alexander. I believe that this collaborative learning is going to be quite important for future deployment of TinyML devices at a scale. And I think there are several TinyML approaches that have been proposed. I was just wondering if what is the fundamental difference between like what the Octonion is proposing and other type of companies, like for example, federated learning and this type of approaches. What is kind of what makes the Octonion approach unique?
I think the unique is what we're trying to achieve is to build unsupervised, fully unsupervised pipeline both at the edge and in the cloud, because in real life, usually people who have some hardware usually do not have any prior information about this hardware. And the task here is to achieve fully automated monitoring phase and perform some predictive monitoring. But in the lack of priori knowledge, unsupervised approach are quite important. Also, we're targeting low power devices like Cortex-M4 from STM or similar, with a low amount of operating memory and low frequency of CPU. So I think that's.
Okay, thank you. And if people would like to learn more about the Octonion devices or kind of try to use them, what would be the way to learn more? What would be the way to use them?
I think the good starting point is to go to octonion.com and check out the information there. And also anyone can please feel free to contact me by mail and ask any questions, and I will try to provide you as much information as possible.
Okay, great, thank you. And in terms of applications, I think you mentioned one example, which is vibrational type of modalities for mechanical. Where do you see this type of approach will be more successful in terms of deployment?
So right now we're targeting most of all vibration analysis, but also we currently developed the sound analysis approach for the use cases when vibration data is not achievable due to some mechanical specialities of the equipment. So this is evolution of the approach, is to analyze the sound data.
Okay, well, great. Thank you. I think this is, again, a very interesting topic, how this multiple tiny devices learn from each other on a field. And I do believe it has a lot of potential. So hope we'll see more development from Octonion in the future. I'd like to acknowledge TinyML Talks webcast sponsor, H-Impulse. Again, if you're interested, please visit their website and see their offerings, their products. And for additional sponsorship, if you're a company or if you're interested, please contact betty@tinyml.org for more information. So next presentations will be, next TinyML talks will be in 2 weeks on Thursday by Facebook on AR and by Synopsys on TensorFlow Lite for microcontrollers. Also 2 very interesting topics for the TinyML community. And as usual, you are going to see announcement and registrations by email and on LinkedIn and Twitter and all the social media and obviously meetups. And also, I should mention and should encourage you to join TinyML meetups. I think we have about 2,000 people as of today, and the community is growing very, very fast. At this point, I would like to thank you, our presenters, and thank you, the audience, for attending TinyML talks. We hope that you found them interesting and useful for what you're doing. If you're interested in participating in any way in TinyML, either presenting or starting meetups, please contact us. For the talk specifically, the email is talks@tinyml.org, and we hope to see you online again in 2 weeks. Thank you all.